All right, let's take a look at 9a. We're supposed to make a careful sketch of y equals minus 2 plus cosine of pi x. If it helps to clarify things, we can rewrite that as cosine of pi x minus 2. Let's start off with a graph of y equals cosine of x. Let's make a quick sketch here. So here is height 1, height minus 1. We'll dot those in. And I'll put in pi over 2, pi, 3 pi over 2, 2 pi. I'll put in minus pi over 2. And we'll sketch cosine, which starts at the top of the curve. Put some points on there that I know that the curve goes through. And let me do my best to sketch something that looks reasonable here. And that continues, of course. Now so this is a graph y equals cosine x. Now on a different set of axes, let's graph y equals cosine of pi x. So again, we'll draw some axes. One and -1. I'll dot in those heights. And we're going to graph y equals cosine of pi x. Now, that pi we can see right away is either going to be a stretch or compression. To figure out which, we notice that it's right in front of the x, so we know it's a horizontal change. You would think that multiplication by pi would mean a stretch of factor of pi, but we know that horizontal changes are opposite to what you'd expect. So instead of having period 2 pi, this has period 2. So it completes one complete cycle in time 2. It's a much more compressed curve. So there's 1, there's 2. So there's a half, there's 1.5. So cos takes 2 pi to go from the top to the bottom all the way back up to the top. This can do it in time 2. So it's the top here, 0 at 1/2. At 1 it's all the way at the bottom. At 1.5 it's here. At 2 it's all the way up there. And of course that continues. Here's, say, -1. Here's -1/2. So it continues to do that oscillation. So let me try to draw this curve now that I've put my values on the x and the y axes. So I can see this is at 2 we're at the top, at 1 we're at the bottom. I've marked my axes very carefully. So it's a much more compressed curve. And now the only thing remaining to do is put the -2 in, which we know is a translation, a shift. This is in the vertical direction because the whole function, we're subtracting 2 from the whole function. And so it's a translation down by 2 units. Let's go ahead and sketch that in. So some axes again. So if we move the whole thing down by 2 units, the bottom goes down to -3. -1, -2, -3, and the top goes down to -1. So I will sketch in y equals -1. And the bottom is at height -3. The middle height is -2. But again, it has the same period as we had over here. It repeats every 2 units. So 1, 2, there's 1/2, 1.5, -1, -1/2. We're at the top. At 1/2, we're in the middle. At x equals 1, we're at the bottom. At x equals 1.5, we're in the middle again, so let me just draw some vertical lines here so we can see where these things fall. At x equals 2, we're back at the top again. So same shape the curve had before, it's just shifted down by 2 units. And this, of course, continues in both directions. All right, now let's take a look at 2 secant x plus 1. Let's begin. Let me move this down. So let's begin with a graph of secant x. We remember secant is 1 over cosine. And while it's not a graph we spent nearly as much time on as sine and cosine, we should know its general shape. 1 over cosine has a vertical asymptote every time cosine is equal to 0. Now cosine is equal to 0 at pi over 2, at 3 pi over 2, at minus pi over 2. So at these values we have a vertical asymptote. Every time cosine is equal to 0, we have a vertical asymptote. So at pi over 2, at 3 pi over 2, at minus pi over 2, we have a vertical asymptote at each one of those points. And we know that we have these sort of right side up and upside down U shapes. Here's height 1, here's height minus 1. Let's dot those in. So y equals secant x. We have this right side up U shape over here. It approaches these lines asymptotically. Let me do my best to sketch this in. Bottoms out at height 1. And then we have this upside down U over here. Tops out at height minus 1. Approaches those lines asymptotically. We have another curve which bottoms out at height 1 again and goes back up, and it just repeats like that. There's another curve over here. I'm not going to try to sketch that in. Now for 2 secant x plus 1, we're going to take the whole thing, sorry, for 2 secant x, so this was y equals secant x. For 2 secant x, we're going to take the whole thing and stretch it vertically. So let's see if we can do that. So pi over 2, pi, 3 pi over 2, 2 pi, minus pi over 2. We're not really playing with the vertical asymptotes at all. But instead of going down to 1 and up to minus 1, so there's 1 and minus 1, since we're stretching everything vertically, we only go down to 2 and minus 2. So let's dot those in. But other than that, we more or less have the same shape we had before. This U now bottoms out at height 2. And this one tops out at height minus 2. And we have another one over here. And so on. And one more. With the plus 1, all we're going to do is shift everything up 1 unit. So instead of bottoming out at height 2 over here, it'll bottom out at height 3. And instead of bottoming out at minus 2 over here, it'll bottom out at height minus 1. So let's see if we can sketch that quickly. So 1, 2, 3, minus 1. I'll dot those heights in. So 3 minus 1. Here we are at pi over 2, pi, 3 pi over 2, 2 pi, Let's dot in the same, here's minus pi over 2. Let's dot in those same vertical asymptotes. And these same U shapes just shifted up from the last graph by 1 unit. Approaching these lines asymptotically, getting closer and closer to, and so on. And that continues. And there we go. So here we have y equals 2 secant x plus 1. Vertical stretch by a factor of 2, vertical shift up by 1 unit. And let's take a look at number 11. We get that to focus. Verify the identity secant x minus cosine x equals sine x times tan x. So let's start with the left-hand side. So the left side equals secant x minus cosine of x, and the right side equals sine x times tan x. And I'm just going to change the whole thing into sines and cosines right now. So secant of x is 1 over cosine of x minus cosine of x. And sine x times tan x, that's sine x. Tan is sine over cosine. So sine x over cosine of x. So what we have over here, we know when we subtract fractions, we're just going to get everything over a common denominator. So this is equal to 1 over cosine of x. This is cosine of x over 1. I want it to be over cosine of x. But if I multiply the bottom by cosine, I have to multiply the top by cosine too. So that would make it cosine squared of x. And what we have over here is sine times sine. That's sine squared x over cos x. What we have over here is 1 minus cosine squared of x over cosine squared of x. Over cosine of x. And we can see that these two look almost exactly the same, except we have a sine squared x over here and a 1 minus cos squared x over here, but we remember that sine squared plus cos squared equals 1. So 1 minus cos squared is equal to sine squared. And now the left side and the right side are the same. And so we've proven our identity. Now remember, not to write equal signs you can't justify. So we haven't done that. We haven't written an equal sign between the left side and the right side until the very end when we can actually justify it. And now we're supposed to take a look at all solutions to 2 sine squared plus cos x minus 1 equals 0 in the interval 0 to 2 pi. Okay, so we can go ahead and write this as, take a look and